So this is a question which is based on the equivalent circuit of two winding transformer. So let me first read the statement of the question. Question is like, the exact equivalent circuit of a two winding transformer is given in the figure below. So this is the below figure which is given in the question. For affecting simplification, the parallel magnetizing branch, which is consisting of RC and XM, is shifted to the left of primary leakage impedance R1 plus GX1. So here RC is the core loss resistance. RC is the representative of core loss, and XM is the magnetizing reactance. XM is the representative of magnetization of the core. XM is the representative of magnetization of transformer core. So now he is saying that he has shifted the parallel magnetizing branch. That means this branch, which is consisting of RC and XM, to the left of this primary leakage impedance R1 plus GX1. Now this simplification introduces the inaccuracy in the neglect of A or B or C or D. These four are the statement. These four are the options, out of which only one option is correct. That you have to choose that correct option after analyzing the circuit. So first option is voltage impedance in the primary voltage. This is drop. This is the drop, voltage drop. So voltage drop in the primary impedance due to the secondary current. Is this correct? Or option B is voltage drop in the primary impedance due to the exciting current. Is this correct? Or option C, voltage drop in the secondary impedance due to exciting current. Is this correct? Or option D is reduction in values of RC and XM of the exciting current. Is this correct? So out of these four options, only one option is correct, and you have to choose that correct option. So just analyze the equivalent circuit of the transformer. So here the supply voltage is V1, R1 is the primary winding resistance, and J times of X1 is the primary winding leakage reactance. I1 is the current in the primary winding. Similarly, in the secondary winding, the winding resistance is R2. When it is referred to the primary side, you can write it R2 dash. And similarly, secondary winding leakage reactance is J times of X2 dash, and I2 dash is the current in the secondary winding. So when you refer the secondary side parameter to the primary side, they will become R2 dash, J times of X2 dash, I2 dash, and V2 dash. So that means by the action of turn ratio, you can refer all the secondary side quantities to the primary side, and you can combine these two primary equivalent circuit with the secondary equivalent circuit. And here at the center you will find that this is the parallel shunt branch, which is consisting of core loss component RC. The current flowing in this RC is IC, and XM is a magnetizing reactance. Im is a magnetizing current which is responsible for the magnetization of the transformer core, right? So now according to the question, you have to shift the parallel branch, this parallel or shunt branch, you have to shift it to the left of primary leakage impedance R1 plus JX1. So that means you have to shift this shunt branch to the left of this primary leakage impedance R1 plus JX1. That means towards the supply side you have to shift this whole shunt branch and then analyze that there will be some error, and due to what the error comes out, that you have to analyze and you have to choose the correct option accordingly, right? So let me shift the parallel magnetizing branch, or the shunt branch consisting of RC and XM to the left of primary leakage impedance R1 plus JX1. When I shift this parallel magnetizing branch to the left of this primary leakage impedance, that means towards the supply side V1, then the circuit will look like this. See here I have shifted this whole shunt branch to the left of this primary leakage impedance R1 plus JX1. So now V1 is applied voltage as before, I1 is the primary winding current as before, and here RC and XM are the shunt branch parameter. RC is the core loss resistance, XM is a magnetizing reactance, IE is the current which is flowing into this shunt branch. IE is basically the exciting current. It is the exciting current. Now remaining part you draw as it is, that means R2 dash is same as R2 dash, JX2 dash is same as JX2 dash, I2 dash is same as I2 dash, V2 dash is same as V2 dash. So simply by shifting this parallel shunt branch to the left of primary leakage impedance R1 plus JX1, the circuit will look like this. Now let us analyze. In this second figure, let me call this is figure 2, and this question figure, let me call this is question figure, let me call this figure number 1. So in figure number 2, that means after shifting of this shunt branch to the left of this leakage impedance R1 plus JX1, it will be the copper loss, let me call it as PCU2 for figure 2. Copper loss, let me call it as PCU2. It is equal to the current which is flowing in the resistive part of the primary and the secondary winding, that is R1 and R2 dash respectively. So here PCU2, that is copper loss in this second figure, will be the current which is flowing in this R1 and R2 dash is I2 dash only, because you have now shifted the shunt branch to the left of primary leakage impedance R1 plus JX1, so it will become I2 dash square in bracket R1 plus R2 dash. So here in place of I1, in place of I2, see here what is this primary current I1. When you apply Kirchhoff's current law at this node, you can write the phasor sum, that is the phasor sum of I2 dash and IE will be equal to primary winding current I1, right? Apply Kirchhoff's current law at this node. Incoming current is I1, outgoing current are IE and I2 dash. Apply KCL, Kirchhoff current law, you will get I1 is equal to IE plus I2 dash. So here I can write I1 is equal to IE plus I2 dash, right? So phasor sum of exciting current IE plus I2 dash will be equal to primary winding current I1. These are basically phasor values because we are dealing with AC. So these are all the phasor values. So phasor sum of IE exciting current plus secondary winding current I2 dash, which is referred to primary side, that's why I2 dash. Phasor sum of IE plus I2 dash will be equal to primary winding current I1. So now analyze the figure number 1. Figure number 1 is this question figure. Here the copper loss will be the power loss into this primary winding resistance R1 and power loss into this secondary winding resistance R2 dash. So current which is flowing in R1 is I1, current which is flowing in R2 dash is I2 dash. So the copper loss in this first figure, figure number 1, it will be equal to I1 square R1 plus I2 dash square into R2 dash. So in place of I1, I am going to put IE plus I2 dash, right? So IE plus I2 dash whole square into R1 plus I2 dash square into R2, right? I2 dash square into R2, right? So now let me analyze further. So I2 dash square you take common, in bracket it will become R1 plus R2 dash plus this will, the remaining parts will be IE square R1. When you open this whole square of IE plus I2 dash, IE square R1 plus 2 I2 dash into R1, these are the remaining terms. I2 dash is common, I2 dash square is common in R1 and R2, so take common, in bracket you write R1 plus R2 dash. So the remaining term plus IE square R1 plus 2 IE I2 dash into R1. So PCU1, now you see analyze that this whole term I2 dash square into R1 plus R2 dash, this whole term is nothing but copper loss in case of second figure. See this, analyze from the equation number 1. We have calculated the copper loss in the second figure because the same current I2 dash is flowing in R2 dash and R1. So copper loss will be I2 dash square in bracket R1 plus R2 dash in figure 2. So this, in place of this I2 dash square in bracket R1 plus R2 dash, you can put PCU2, copper loss in the figure 2, plus the remaining term write as it is, IE square R1 plus 2 IE I2 dash into R1. So you just analyze, PCU1 is the copper loss for the figure 1, PCU2 is the copper loss for figure 2. Which one is greater? Just analyze which one is greater. You can analyze that copper loss so when you add IE square R1 plus 2 IE I2 dash into R1 in copper loss for the second figure, that is PCU2, then it will become equal to PCU1. So obviously you can write PCU2 is less than PCU1. That means copper loss for the second figure will be less than copper loss in this figure number 1. So PCU2 is less than PCU1, that means copper loss will decrease. That is the first result that you can analyze by the shifting of this parallel shunt branch towards the left of primary leakage impedance R1 plus GX1. So by the shifting of this parallel shunt branch to the left of this R1 plus JX1, you have analyzed that the copper loss will reduce. Now just analyze for the core loss. Just have a look at it. In the figure number 1, the voltage which is appearing across this shunt branch, that means across this point and this point, the voltage which is appearing is V1, applied voltage V1 minus I1 in bracket R1 plus Jx1. That means V1 minus drop in this primary winding leakage impedance will appear across the shunt branch for the figure number 1. Right? When you have not shifted this shunt branch, that means when the shunt branch is at the center in the figure number 1, then voltage appearing across this shunt branch is V1 minus I1 in bracket R1 plus Gx1. So voltage appearing across shunt branch is V1, applied voltage V1 minus I1 R1 plus Gx1. So these are all phasor values, right? Because we are dealing with AC, needless to say, right? So V1 minus the voltage drop in the primary impedance will appear across the shunt branch, right? Now analyze figure 2. In figure 2, what is the voltage appearing across the shunt branch when you have shifted the shunt branch to the left of this primary leakage impedance R1 plus X1? That means when the shunt branch is across the supply side, then the voltage appearing across this shunt branch is nothing but supply voltage only, right? That is V1. So whole V1 will appear across the shunt branch because you have shifted the shunt branch towards the supply side or to the left of this primary leakage impedance R1 plus Gx1. So in figure number 2, voltage appearing across shunt branch is equal to V1 only. So you just compare, this is V1 minus R1, this is V1 minus R1, right? This is V1 minus I1 R1 plus Gx1, and this is V1. So which one is more? Obviously this V1 is more. That means voltage appearing across the shunt branch in figure number 2 will be more, and it will be more than V1 minus I1 bracket R1 plus Gx1, which is the voltage drop which is appearing across the figure number 1 across the shunt branch. So the core loss, which basically consists of eddy current loss, and eddy current loss is proportional to applied voltage square, right? So here you analyze that since the voltage appearing across the shunt branch is more in the second case, that means in the figure 2, so that means core loss, that is applied voltage square, PC is equal to applied voltage square divided by core loss resistance RC, right? So core loss will be more for the second case, that means for figure number 2. So that's why P core 2 greater than P core 1, right? So core loss will increase for the second figure, right, when you have shifted the shunt branch towards the supply side or towards the left of primary leakage impedance R1 plus Gx1. So that means after shifting of this shunt branch you have analyzed, right? So clearly the inaccuracy will be due to the voltage drop in the primary impedance due to the exciting current, right? So which option is correct? Which option is correct? Option B is correct. So here option B is the correct option, that you have to conclude, that option B is correct option. So this B option is correct. So thank you very much. Thanks for watching.